This video extends on the semantics for QL and introduces the idea of constructing models to show that sentences are contingent. Recall that in the semantics for QL, the structure that specifies the truth value of a sentence is a model. A model specifies a universe of discourse, an extension for every predicate, and a referent for every constant. Given a model and a sentence, we can figure out the truth value of that sentence in the model. Suppose, for example, we have this model. The universe of discourse is the set containing 2 and 4. The extension of D, one place predicate D, is the set containing 2, and the extension of Q is the set containing 4. And we want to evaluate this sentence, exists X, dx, and qx. We consider whether there's any member of the universe of discourse that satisfies the subformula d blank and q blank. The existential quantifier is making the claim that at least one of them does. Note that the things we've written over on the right-hand side aren't sentences exactly, because 2 and 4 are objects in the universe of discourse, rather than symbols of QL. But we're asking what happens if you plug those objects in the place of X. Well, 2 doesn't satisfy the subformula. It yields a value of 0. 4 doesn't satisfy the subformula. It yields a value of 0. So, regardless of which object you're looking at, you get a value of 0 for the subformula. And that means the existentially quantified sentence is false. There isn't an X which satisfies dx and qx. So, sentence false. Now, the reverse is also true. We can work in the other direction. Given a sentence, we can construct a model to give it any possible truth value. For example, we might have this instruction. Construct a model in which exists X, dx, and qx is false. The model we already had would work. That is, we just saw a model in which this sentence comes out false. Or we could make an even simpler model, like this one. Let the universe of discourse be the set containing Albany. Let the extension of D be empty. Let the extension of Q be empty. Note that I don't have any symbolization key in mind at all here. I've just chosen elements of the model, the universe of discourse, and extensions for the predicates, so that it yields the result we want. This model does make the sentence false. Of course, the structural fact that matters about this model is that the universe of discourse has one member. Now, in this case, I've made it Albany, but any one member would do just as well. For example, we could have the universe of discourse be the set containing the number 1. The extensions of the two predicates would be the same. The resulting truth values would be the same as well. So there's something tricky about working in this direction. I said that given a sentence, we can construct a model to give it any possible truth value. But which truth values are possible? Consider this sentence. For all x, px or not px. We can make it true easily enough. You might want to pause the video and confirm that this model makes the sentence true. The trick is that this sentence would be true regardless of what model we constructed. In fact, for all x, px or not px is true in every model. In English, we had a name for a sentence like this. A tautology is a sentence that must be true, just as a matter of logic. For a sentence to be a tautology in QL means that it's true in every model. So, for all x, px, and not px is a tautology. But how could we show that it's a tautology? In SL, we had truth tables, and we could construct a complete truth table because we could list all the possible truth value assignments that could make a difference for the value of a sentence. For example, if we had 2 sentence letters, we could make a 4-row truth table with the possible combinations of 1s and 0s. However, we can't show that a sentence is a tautology by listing all the possible models, because there are infinitely many possible models. The universe of discourse might have one thing in it. It might have two things. It might have three things. It might have four, five. It might have infinitely many things. There's no way we can write down all the possible, formally relevant universes of discourse. And that means there's no way to write down all the possible models. Of course, we could try to think it through. We could reason in this way. For every object in the universe of discourse, it's either in the extension of P or it's not. If it is in the extension of P, then P blank is satisfied for that object. If it's not, then not P blank is satisfied. In either case, P blank or not P blank is satisfied. So P blank or not P blank is satisfied for every object in the universe of discourse. It's getting a value of 1 for everything, regardless of what it is. And that makes, for all x, px or not px true. This reasoning holds regardless of what the universe of discourse is. So for all x, px or not px is true in every model. And that's just what it means to be a tautology. That paragraph does show that the sentence is a tautology, but it's awkward. And in general, it's awkward to try and show that a sentence is a tautology. If we have to construct paragraph length arguments, it really undercuts the whole motivation for why we started formalizing in the first place. On the other hand, showing that a sentence is not a tautology just requires providing one model in which it's false. We already know how to do that. That's what we were doing back at the beginning of this video. Recall that in English, a contradiction is a sentence that must be false, just as a matter of logic. For a sentence to be a contradiction in QL means that it's false in every model. Showing that a sentence is a contradiction would require reasoning about every possible model. And that means it's awkward to show that a sentence is a contradiction, just in the same way it's awkward to show that a sentence is a tautology. However, showing that a sentence is not a contradiction just requires providing one model in which the sentence is true. Recall that in English, a contingent sentence is one that is neither a tautology nor a contradiction. A contingent sentence of QL, similarly, is one that is neither a tautology nor a contradiction. So to show that a sentence is contingent, we just need to show that it's not a tautology and also that it's not a contradiction. Showing that a sentence is contingent just requires providing one model in which it's true to show that it's not a contradiction, and another model in which it's false to show that it's not a tautology. This won't always be easy, but it's something we know how to do. To show that a sentence is contingent, construct two models, one in which it's true and another in which it's false. Suppose we have this problem. Show that RAB is contingent. Let's start with a simple model and put just one thing in the universe of discourse, say the number 1. Recall that R is a two-place predicate, and that means its extension will be a set of pairs. The pair 1, 1 can either be in the extension of R or not. We'll put it in. Okay, we've got a model. And the sentence is true in this model. So that does one of the things we need to do. What if we make the extension of R be empty? That gives us a different model. And it's false in the second model. So we're done. We got lucky because the first two models we tried did what we wanted. If the sentence had the same truth value in both of these, we could only have used one of them. We'd have to try more combinations. We could have tried adding a second thing to the universe of discourse. Sometimes a little trial and error is required. The video has covered constructing models to make a particular sentence true or false. By constructing two models, we can show that a sentence is contingent. In the next video, we'll talk about constructing models to show that arguments are invalid.